Welcome to this walkthrough of LeetCode problem number 712, minimum ASCII delete sum for two strings. In this problem, we'll explore how to minimize the ASCII delete sum required to make two strings equal. Let's dive into the problem and break it down step by step. In this problem, we are tasked with making two given strings, S1 and S2, equal by deleting characters from either string. The cost of deleting a character is equal to its ASCII value. Our goal is to find the minimum total ASCII value of the characters that need to be deleted to make the two strings identical. For example, if S1 is C and S2 is EAT, the cost of deletion is calculated based on the ASCII values of the removed characters. The input consists of two strings, S1 and S2, each containing only lowercase English letters, and their lengths can range from 1 to 1000. The output is a single integer representing the minimum ASCII deletion cost. Let's explore some examples to better understand the problem requirements. Consider the first example with S1 as C and S2 as EAT. To make the two strings equal, we can delete the character S from S1 and the character T from S2. The ASCII value of S is 115, and the ASCII value of T is 116. Adding these values gives a total cost of 231. Now, if we look at another example where S1 is delete and S2 is LEET, we can delete the characters D and E from S1, as well as 1E from S2. The ASCII values of these characters are 100, 101, and 101 respectively, resulting in a total cost of 403. These examples illustrate how the deletions and their corresponding costs are determined to make the strings equal. In the third example, S1 is ABC and S2 is DEF. Since there are no common characters between the two strings, we must delete all characters from both strings to make them equal. The ASCII values of A, B, and C are 97, 98, and 99, respectively, while the ASCII values of D, E, and F are 100, 101, and 102. Adding these values gives a total cost of 597. This example highlights a scenario where the strings have no overlap, and the solution involves removing all characters. Additionally, the problem has constraints that require us to handle input strings up to a length of 1000, and we need an efficient solution with a time complexity of O, and *m, or better. To further clarify, let's examine some edge cases. First, if the strings have no common characters, such as S1 being ABC and S2 being XYZ, all characters must be deleted, resulting in a cost that equals the sum of their ASCII values. Second, if one string is empty, like S1 being ABC and S2 being empty, the cost is simply the sum of the ASCII values of all characters in S1. Third, if the strings are already equal, such as S1 and S2 both being ABC, no deletions are needed, and the cost is 0. Finally, if the strings have repetitive characters, like S1 being AAAA and S2 being AA, the extra characters must be deleted, and the cost depends on those deletions. To solve this problem, we can use a dynamic programming approach. We define a 2D DP table where DP, I, J, represents the minimum cost to make the first I characters of S1 and the first J characters of S2 equal. The base cases handle situations where one of the strings is empty, and the recursive relation determines whether to delete characters or keep them based on their equality. To implement the solution, we start by defining a DP table with dimensions, len, S1, plus 1, x, len, S2, plus 1. The base cases are initialized such that if one string is empty, the cost equals the sum of ASCII values of the other string. Then, we fill the DP table using the recurrence relation. If the current characters of S1 and S2 are equal, DP, I, J, is set to DP, I1, J1, since no deletion is needed. Otherwise, the cost is the minimum of two options, deleting the current character of S1, or deleting the current character of S2. These options are represented by DP, I1, J, plus the ASCII value of S1, I1, and DP, I, J1, plus the ASCII value of S2, J1, respectively. Finally, the value at DP, len, S1, len, S2, gives the minimum cost to make the two strings equal. This approach ensures we efficiently compute the solution for all substrings of S1 and S2. In this problem, we aim to minimize the ASCII delete sum required to make two strings equal. To solve this, several approaches can be considered. First is the brute force approach, which uses recursive exploration. The intuition here is to try all possible combinations of deletions for both strings, calculating the total ASCII sum for each case. For every character in the strings, we have two options: either delete it from the first string or delete it from the second. If the current characters match, we simply move both pointers forward in the strings. Otherwise, we recursively calculate costs by deleting one character at a time. While this approach is straightforward to describe, its exponential time complexity, 2m plus n, makes it impractical for larger inputs. To improve on this, we turn to the dynamic programming approach, which takes advantage of the problem's optimal substructure. By avoiding recomputation of overlapping subproblems, we use a table to memorize results, significantly improving efficiency. The idea is to build a 2D DP table where each entry represents the minimum ASCII delete sum required to make certain substrings equal. Let's explore how this is implemented in detail. In the dynamic programming approach, we define a 2D DP table DP, I, J, where each entry represents the minimum ASCII delete sum required to make the substrings S1, 0, I, and S2, 0, J, equal. For the base case, if one of the strings is empty, the cost is simply the sum of the ASCII values of all remaining characters in the other string. When transitioning between states, if the current characters of both strings match, we inherit the result from DP, I1, J1, since no deletion is needed. However, if the characters differ, we calculate the minimum cost by either deleting the character from the first string or from the second. This is represented by the formula dp I, j equals min dp I1, j plus ASCII S1, I1 dp I, j1 plus ASCII S2, j1. At the end, the value stored in dp m, n, where m and n are the lengths of the two strings, gives us the result. The time complexity of this approach is m*n, because we fill the entire table, and the space complexity is also m*n, due to the 2D array. To optimize space, we can further reduce the memory usage by recognizing that only the previous row is required to compute the current row. Using a rolling array, we can bring the space complexity down to n, while maintaining the same time complexity. Given the options, we chose the dynamic programming approach because it strikes a good balance between simplicity and efficiency. While the brute force approach is conceptually easy to understand, its exponential complexity makes it computationally infeasible for larger inputs. On the other hand, the space-optimized DP approach builds upon the standard DP solution by reducing memory usage, making it more suitable for scenarios with large input sizes. However, its rolling array implementation can be slightly less intuitive for beginners. A key insight in solving this problem was recognizing its similarity to the longest common subsequence (LCS) problem, but with the additional twist of accounting for ASCII values instead of just counting characters. By framing the problem as minimizing deletion costs, we could systematically leverage dynamic programming to find the optimal solution. Overall, the space-optimized DP approach provides the best trade-off between performance and scalability, making it the preferred solution for this problem. The problem we are solving is LeetCode number 712, where we need to find the minimum ASCII delete sum required to make two strings equal. To do this, we aim to minimize the cumulative cost of deletions based on the ASCII values of the characters. The solution begins with defining a recursive relation. We denote the two strings as S1 and S2, with lengths n and m, respectively. The key idea is to define a function dp I, j, that represents the minimum ASCII delete sum needed to make the substrings S1, I and S2, j equal. Next, we establish the base cases. If we have processed all characters in S1, meaning I equals n, then we must delete all remaining characters in S2, summing their ASCII values. Similarly, if we finish processing S2, we sum the ASCII values of the remaining characters in S1. These base cases set the foundation for our recursive approach to handle the problem step by step. Now let's address the recursive cases. If the characters at the current indices I and j in S1 and S2 are equal, there's no need for deletion, and we simply move to the next pair of characters by computing dp I plus 1, j plus 1. However, if the characters differ, we consider two possible actions. First, we could delete the character S1, I, incurring a cost equal to its ASCII value ord, S1, I, and solve for the subproblem dp I plus 1, j. Alternatively, we could delete the character S2, j, with a cost of ord, S2, j, and solve for dp I, j plus 1. The optimal solution at dp I, j, is the minimum of these two options. To transition from the recursive approach to dynamic programming, we use a 2D array DP to store the results of all subproblems, ensuring we avoid redundant calculations. The base cases are initialized by pre-computing the ASCII sums for the remaining characters when either string is fully processed. The DP table is then filled in reverse order, starting from the smallest subproblems, until we calculate the result for the entire strings. The solution to the problem is stored in DP 0, 0, which gives the minimum ASCII delete sum required to make the two input strings equal. There are several key insights that make this approach effective. First, the recursive structure of the problem allows it to be broken down into smaller, manageable subproblems, which is why dynamic programming is a natural fit. Second, the dependencies in the DP state are limited to DP I plus 1, j, and DP I, j plus 1, which simplifies computation. Third, by storing intermediate results in the DP table, we avoid recalculating solutions for the same subproblems, significantly improving efficiency. This reduces the time complexity to O and *m, where n and m are the lengths of the two strings. Additionally, the problem's unique aspect is that deletion costs are determined by ASCII values, distinguishing it from standard string alignment problems. The primary data structure used here is the 2D DP array, which requires O and *m space. However, this can be optimized further. The ASCII values are computed using Python's ORD function, which makes the implementation straightforward. To optimize space usage, we can replace the full 2D DP table with a rolling array that only stores two rows, one for the current state and one for the previous state. This reduces the space complexity to O, min, n, m, while maintaining the correctness of the solution. When handling edge cases, the approach remains robust. If one or both input strings are empty, the result is simply the sum of the ASCII values of all characters in the non-empty string. If the strings are identical, no deletions are needed, resulting in a cost of 0. On the other hand, if the strings share no common characters, the solution involves deleting all characters from both strings, yielding the total sum of their ASCII values. With these optimizations and considerations for edge cases, the algorithm is both efficient and comprehensive, providing an optimal solution to the problem. Here, we start by defining the function minimum delete_sum within the solution class. The inputs are two strings, s1 and s2. We determine their lengths, n and m, respectively, and initialize a 2D list DP with dimensions, n plus 1, x, m plus 1, filled with zeros. This table will help us store the minimum ASCII delete sums for different substrings of s1 and s2. Next, we populate the first row and the first column of the table. For the first row, we calculate the cumulative ASCII values of characters from s2, simulating the scenario where all characters in s2 are deleted. Similarly, for the first column, we compute the cumulative ASCII values of characters from s1, representing the cost of deleting all characters in s1. After setting up these base cases, we proceed to fill the rest of the table. For each cell in the table, we compare the characters of s1 and s2. If the characters match, no deletion is needed, so we copy the value from the diagonal cell. Otherwise, we calculate the minimum cost by either deleting a character from s1 or s2, and we update the cell accordingly. Finally, after filling the entire table, the result is stored in the bottom right cell, DP, n, m. This cell contains the minimum ASCII delete sum required to make the two input strings equal. We return this value as the output of the function. This completes the implementation, and the dynamic programming table ensures that we efficiently compute the solution by reusing overlapping subproblem results. Here, we begin by defining the minimum delete sum method, which takes two strings, s1 and s2, as inputs. The lengths of these strings are stored in variables n and m. Next, we initialize a 2D dynamic programming table, DP, where DP, I, j, will eventually represent the minimum ASCII delete sum required to make the first I characters of s1 and the first j characters of s2 equal. To handle the base cases, we fill the first row of the table. This represents the scenario where we only delete characters from s2 to match an empty s1. For each column, we add the ASCII value of the corresponding character from s2 to the previous column's value. Similarly, we fill the first column to handle the case where we delete characters from s1 to match an empty s2. For each row, we add the ASCII value of the corresponding character from s1 to the previous row's value. With the base cases set, we proceed to populate the rest of the table. Now, we continue to fill the DP table for the cases where both strings have characters. For each pair of indices I and j, we check if the characters s1, I1, and s2, j1, are the same. If they match, no deletion is needed, so we inherit the value from DP, I1, j1. If they don't match, we calculate the cost of deleting the character from either s1 or s2. Deleting from s1 adds the ASCII value of s1, I1, to DP, I1, j, while deleting from s2 adds the ASCII value of s2, j1, to DP, I, j1. We take the minimum of these two options and assign it to DP, I, j. After completing the table, the final result, which is the minimum ASCII delete sum to make the two strings equal, is stored in DP, n, m. This value is returned as the output of the method. In this problem, we are tasked with determining the minimum ASCII delete sum required to make two strings identical. To solve this, dynamic programming plays a crucial role, as it allows us to break down the problem into manageable subproblems. Let's consider the example where s1 is C and s2 is EAT. The first step involves initializing a dynamic programming table, or DP table, with dimensions n+1 and x, m+1, where n and m are the lengths of s1 and s2 respectively. Here, both strings have a length of 3, so the table's dimensions are 4 by 4. We start by filling the first row, which represents the cost of deleting characters from s2 to reach an empty string. For instance, deleting the first character e from s2 gives us a cost of 101, the ASCII value of e. Adding the cost of deleting n and then t, we calculate the cumulative values in the first row as 101, 198, and 314, respectively. This initialization helps establish the baseline costs when one string is empty. Next, we populate the first column of the DP table, which accounts for the cost of deleting characters from s1 to reach an empty string. Deleting s, for instance, incurs an ASCII value cost of 115, followed by adding the ASCII value of e to get 216, and then adding the value of a to arrive at 313. With the first row and column initialized, we begin filling the rest of the table. For each cell DP, I, j, we compare the characters s1, I1, and s2, j1. If the characters are not equal, we consider two options, deleting a character from s1 or deleting from s2, and we choose the option with the minimum cost. For example, in the cell corresponding to I equals 1 and j equals 1, s and e are not equal. The cost of deleting s is 216, and the cost of deleting e is also 216, so we update the cell with the minimum value, which is 216. This process is repeated for all other cells until the table is fully populated. The final value at DP, 3, represents the minimum ASCII delete sum for making C and E equal, which is 231. Let's now consider a slightly more complex example where S1 is delete and S2 is leet. The lengths of the strings are 6 and 4, respectively, so the DP table will have dimensions 7 by 5. As before, we begin by initializing the first row and column. The first row represents deleting all characters of S2, while the first column represents deleting all characters of S1. Each cell in the row and column accumulates the ASCII values of the characters deleted. Once initialized, the remaining table is filled by comparing the characters at each position. For instance, at I equals 1 and j equals 1, the characters d and l do not match. Here, we calculate the cost of deleting d and the cost of deleting l, and store the minimum value. However, when we reach I equals 2 and j equals 2, the characters e and e match. In this case, no deletions are required, so we inherit the value from the top left diagonal cell, DP, 1, 1. This process continues for all positions, ensuring that at every step, we minimize the ASCII delete sum using the optimal choices. Once the table is fully populated, the value at DP, 6, 4, gives us the minimum ASCII delete sum for delete and leet, which is 403. This result is derived by systematically considering every possible deletion sequence while retaining only the minimum cost solutions. The key insight here is the structure of the dynamic programming table, where each cell DP, I, j, represents the minimum cost for making the substrings S1, I, and S2, j, equal. The base cases handle scenarios where one string is empty, accumulating the ASCII sum of the other string. The transitions depend on whether the characters match. If they do, we inherit the value from the diagonal cell, and if not, we choose the minimum cost of deleting from either string. The time complexity of this approach is O, and *m, due to the nested loops, and the space complexity is also O, and *m, for storing the DP table. By leveraging dynamic programming, we ensure an efficient and optimal solution for this problem, considering all possible deletions while minimizing the total ASCII cost. The time complexity of this solution is determined by the size of the dynamic programming table and the operations required to populate it. First, we initialize a 2D table with dimensions n+1 by m+1, where n and m are the lengths of the input strings. This step involves iterating over every cell in the table, resulting in O, and *m, time. Next, the first row and column of the table are filled to account for cases where one of the strings is empty. Filling the first row requires m iterations, and filling the first column requires n iterations, giving a combined time complexity of O, n plus m, for this part. The main work occurs when we fill the rest of the table using nested loops, where the outer loop runs n times and the inner loop runs m times. Each cell computation involves constant time operations, like comparing characters and taking the minimum. This step also takes O, and *m, time. Since the dominant term is O, and *m, the overall time complexity of the solution is O, and *m. The space complexity of this solution is driven by the dynamic programming table as well. The table has n+1 rows and m+1 columns, requiring O, and *m, space to store all intermediate results. Additionally, we use a few auxiliary variables, such as n, m, I, j, and loop counters, which require constant space, or O1. Since the DP table dominates the space usage, the overall space complexity of the solution is O, and *m. When comparing this optimized dynamic programming approach to the brute force method, the efficiency gains become clear. A naive solution would involve exploring all possible deletion combinations for both strings, leading to a time complexity of O, 2 to the power of n * 2 to the power of m. This arises because for each string, there are 2 to the power of n or 2 to the power of m subsets of deletions to consider. Such an approach quickly becomes infeasible as the input size grows. By contrast, the dynamic programming solution leverages overlapping subproblems and the optimal substructure property to reduce the time complexity to O, and *m. This is a significant improvement, as we avoid redundant computations by storing intermediate results in the DP table. Importantly, the time and space complexity of this approach remain O, and *m in the best, average, and worst cases, since the structure of the DP table and the number of operations required do not change based on the content of the input strings. To confirm the time complexity mathematically, consider the nested structure of the loops. The outer loop runs n times, and for each iteration of the outer loop, the inner loop runs m times. This results in a total of n *m iterations. Within each iteration, constant time operations such as comparing characters and calculating the minimum are performed. Since the work done in each iteration is constant, the total amount of work is directly proportional to n *m. Therefore, the overall time complexity is O, and *m, validating our earlier conclusion. This formal analysis demonstrates that the dynamic programming solution efficiently handles the problem within the stated complexity bounds. When tackling this problem, there are several common mistakes to watch out for. First, not handling edge cases, like when one or both strings are empty, can lead to runtime errors or incorrect results. If one string is empty, the ASCII sum of the other string should be returned since all characters need to be deleted. Second, it's easy to confuse the indices when implementing recursion or filling out the DP table. Always ensure the relationship between the indices of the two strings, I4S1 and J4S2, is consistent. Third, relying on a naive recursive solution without memoization is another common pitfall. Without memoization, the solution becomes exponentially slow, often resulting in a time limit exceeded error. Finally, improper initialization of the DP table can cause issues. The first row and column represent the ASCII sums required when one string is empty, so initializing these correctly is critical for the algorithm to work as expected. Another mistake to avoid is miscalculating ASCII values. Subtle bugs can arise if you mishandle operations with ORD S1 I or ORD S2 J, so double-check that you're using the correct characters. From an interview perspective, this problem is a variation of the longest common subsequence problem. Instead of optimizing for the length of the subsequence, you're optimizing based on ASCII values. Recognizing this pattern can guide you toward a dynamic programming solution. During interviews, discuss the trade-offs between recursion with memoization and iterative DP. Recursion is often easier to write but uses more memory, while iterative DP is more efficient but slightly harder to implement. Space optimization is another great topic to mention, as you can reduce the DP table from O(m*n) to O(min)(m)n by only storing the current and previous rows. Lastly, ensure your solution is correct before worrying about optimization. Edge cases and base cases should be your top priority, as interviewers value correctness most. This problem is closely related to others that can help strengthen your dynamic programming skills. For example, LeetCode 1143, the longest common subsequence problem, builds intuition for working with subsequences and DP. Similarly, LeetCode 583, delete operation for two strings, focuses on minimizing deletions but doesn't involve ASCII values, offering a simpler variation. LeetCode 516, longest palindromic subsequence, is another subsequence problem that emphasizes identifying and solving for specific patterns within a string. Lastly, LeetCode 1035, uncrossed lines, is a variation of LCS that reinforces the same core principles of subsequences and dynamic programming. Practicing these problems can deepen your understanding of the techniques and patterns used here. There are several approaches to solving this problem, each with its pros and cons. The recursive approach with memoization is intuitive and straightforward to implement, but it comes with high memory usage due to the memoization table and the risk of stack overflow for deep recursion. Iterative dynamic programming avoids recursion depth issues and is more efficient overall, but it can be slightly more complex to implement, especially when optimizing space. Space-optimized DP reduces the space complexity from O(m*n) to O(min)(m)n by storing only the current and previous rows. However, this requires careful indexing, which can make debugging harder. Finally, while greedy approaches are appealing for their simplicity, they don't work here because this problem requires global optimization rather than local decisions. Understanding these trade-offs allows you to adapt your solution to different constraints or interview scenarios effectively. Great job following along. In this problem, we used dynamic programming to solve a classic string manipulation challenge. Remember the importance of optimizing both time and space complexity when designing solutions. Thanks for watching, and don't forget to like and subscribe for more tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!